Okay, fluid mechanics lesson 2, topic 2, hydrostatic fluid pressure. What does this topic comprise? Comprise is there are five things. First is the pressure variation while fluid is at rest, and then incompressible and compressible when you apply this concept into compressible or incompressible fluid. And then for pressure wise, you have the measurement and classification of pressure. Typically, it is dealing with the P gauge and absolute and everything. And then for measurement techniques, we can use three different methods, which are three different type of instruments. I would say they have their own individual formulas, and we're gonna derive it. So it's a little bit tedious over here. While also in this portion, and in fact, this whole topic requires a lot of derivation. So let's start off with the first derivation, which is really something troublesome. Is pressure variation while fluid is at rest. Okay, so give me a moment. Okay, so there will be a body force and a what do you call it, surface force. If you remember from the last few videos, we talk about the fluid forces has two force, body force and a fluid force. I mean surface force. So the body force itself, in this case, although it's if you remember, is mg. Okay, but in our case, the mass itself is a small mass. Okay, a small mass multiplied with the gravity itself. So the small mass itself can be rewritten as equals to rho and then dv, which is the volume. So if you remember, the density equals to mass over volume. So this is the equation. You just sub it in, it's pretty easy. And then it's just a change of the volume itself will cause a change in the weight. Okay, this is what it means for the body force. So I hope you can understand. And then for surface force is complicated. Okay, but hope I can give you an understanding. So okay, the body force will have a one, two, three, four, five. We have a six-sided. Okay, one, two, three, four. Yeah, six-sided cube. Okay, so this six-sided cube is actually being, if you are submerged into the water, there will be a pressure against all sides of the cube itself. Okay, so this cube itself, we will assume that this cube is a water molecule or a water cube, I would say. And yeah, so what we are trying to do, our main objective in the end is trying to derive our specific weight. Okay, so it's gamma equals to W over V or whatsoever. I mean gamma equals to rho G, sorry. Okay, so yeah, so if you were to take into account that the FL force at the L, so this is the force. Okay, so imagine this is the force in this direction, and there will be a PR, which is force R also. Okay, if you remember, force is equals to pressure over area. Okay, so pressure is equals to force times area. So apparently this is you give me a minute, hold on. It is force over area equals to P. I actually write wrongly, so I think wrongly also. So apparently when you bring this A out, force is equals to pressure times the area. So the area is a small set of dy and dz. Okay, so it's in this plane. Okay, in this plane. So you are applying a force perpendicular to this plane. Okay, so the force itself, one force is force L and one force is force R. You are trying to force. The resultant force should be in the x direction. Okay, should be in the x-axis, but I think they actually write wrongly. So it's y direction in this case. I mean, for their case, I don't know whether is it true, but from what I think intuitionally, if you were to push this in this manner and you push this manner, the resultant should be in the x-axis, right? So I believe this is x. Okay, so the resultant should be this. Okay, and in fact this is fx. Later, maybe when we're deriving the formula itself, maybe we can see how it goes. And then this is x times the area itself. So you will eventually get this. Similarly, sorry. Similarly for the y direction. Okay, for the y direction, um, it's the same. You have a force. In this case, is P and B. Sorry, y direction is not this. It's this. Sorry, it's in this direction. There is a force. There is a pressure. Okay, F and pressure B. Okay, so similarly, this is pressure. This is area. So the resultant force should be in the y direction. Okay, and then now the purpose of this is to set up equations, set up a series of equations so that you can actually derive the specific gravity. And then for the last one, z direction is a little tricky, so you have to add in the body force itself. You remember, because the z direction is the height, it deals with the height itself. So this is the t, okay, this is the d. The resultant force should be in the z-axis, which they actually write it correctly. But however, there will be a body force itself, which is minus mg. They take the convention that going down is negative, going up is positive. This also explains why Fd is positive, going up is positive, going down is negative. And then you dW, a small change of W is actually a small change of volume. Sorry. Oh, okay, it's a small change of volume itself. I hope I didn't spoil the mic. And yeah, so the small change of volume is actually we derive from here, the number one, the body force. So with this set, then you give me a minute. From this onwards is trying to set up an assumption. So we will assume that the fluid is at rest, and then therefore is equilibrium. And with this equilibrium conditions, our assumption itself, maybe I would just show you where's my picture. Okay, so let's use this picture to explain what this describes. So we would see that the small change in the force of x, okay, in the x direction and the y direction, okay, the changes in the x and the changes in the y, okay, in this and this is zero because equilibrium, right? Okay. And therefore, if you remember the equation just now, in the x direction, the resultant force can be described using this formula. So is equals to 0. So if dy and dz is not 0, okay, then pr and minus pr is equals to 0. What I mean is that dy and dz definitely cannot be 0 because if you have no area, then how the hell you apply a pressure? So definitely you have the pressure, the same pressure can eventually let it to be equilibrium, and therefore we can deduce that PL is equals to PR, and which is also being described over here. PL is equals to PR, and subsequent, this one is for the in the x direction, okay, PL and PR. However, they write y direction. I still also don't know why, but later maybe in the later part you can know why. So similarly for the x direction, I mean for the y direction, PF and PB should be equals, right? And taking the area is not 0. So with this condition, we can actually set up an equation. Actually for z direction only. So haven't yet. So this is it first, and then now for z direction. Z direction is a little complicated. It deals with a lot of things. So similarly, PD minus PT. This is the formula that we have it over here. Is this one? Okay, for the z direction, as I say, it's a surface force minus the body force. So it's slightly complicated. And then eventually we have this equation, and the dv can be expanded. Okay, the dv, as you can see, our dv over here is expanded to rho dx, sorry, to dx dy in dz, a small change in terms of xyz. Okay, and then the next step itself, we kind of take that dx and dy are so-called, the pressure does not change in x and y direction. So give me a minute. Okay, since we have described that the pressure F and B and L and R are equals, therefore there will be no movement in a x and a y-x direction, and therefore we can deduce that the x and y can be taken as a 1, or some as a constant, or perhaps we can actually, because they are constants, they are the same ds and dy, so we can actually eliminate them off. So therefore we have only left over with the change in dz only in the z direction, and then you bring this function, I mean this whatever your formula towards this side. Okay, just changing the sign, just bring it to the 0, and then you rearrange, and then you okay, give me a minute. Okay, so yeah, you rearrange, you just bring the dz downwards. Okay, the rho g stays, and then now you switch the sign, you just multiply with minus, so you just switching the signs only. Okay, so eventually you get this, and the change in dp, okay, the change in the z direction, dp, and hold on, you can check it out. What is it? The pressure at T minus the pressure at D, okay, is can be governed by this formula, dP and dZ. I mean dP over dZ. So the change over the small change of the z direction. So the change of pressure over the change in the depth of the water. And then you bring this negative to this equation, to here, and this is the rho g, and therefore this minus rho g is a the negative, meaning is downwards, because the gravity itself is, as you know, it's going downwards. So the pressure, it makes sense that saying that the pressure, the bigger the change in pressure, the higher the the higher the density downwards. Okay, the bigger the change in pressure. That is what it means. Okay, so if you were to take another account, so hold on a while. So density is equals to mass over volume, am I right? So density is proportional to mass. So if the mass is heavier, and so m times g downwards is minus, right? So if it's going down, we're gonna have a change. So the reason why we change this sign, pt minus pd, from pd minus pt. Okay, this p, because this equation states that the pressure itself is higher than the pressure that are going downwards, which is untrue, because there's a gravity. Gravity itself definitely will make this whole cube sinks down. So that's why we change the sign. Okay, and then you will derive the specific weight. D equals to minus gamma. Okay, rho g, we can say that this is gamma, and the gamma itself can be rewritten as this, as described over here. So the gamma equals to because as you know, it's rho g, right? So it's just mg over v. Okay, rho is mg over, I mean rho is equals to mass over volume, while rho times g is equals to mg over volume. So therefore, yeah, that's this yeah. So yeah, I think you get what I mean now. Okay, so this can be rewritten as this in few forms, and then this will end my part for deriving specific weight formula and the introduction to body force and surfaces force. Okay, this is just a slight introduction to to the what they call pressure variation while fluid is at rest. Because this is an assumption, we assume that the fluid is equilibrium, so that's why we can derive specific weight. So if it's not equilibrium, I don't know. So yeah, see you in the next video.